welcome to East Prague. Today, as the introduction says, we're going to talk about Orbitport, the gateway to space. So a bit about me, I'm coming with, let's say, unrelated background from SAP, mostly in the cloud domain. I was an architect there, then in SSV network, a bit low-level crypto and Web3, and then in Chainlink. And I've joined SpaceComputer, mostly working on, as I said here, distributed systems, confidential computing, and of course, space, satellites, embedded systems. We are now like in the process, we're still, let's say, pretty much newbies in the area. We're still learning. So there is lots of interesting things to see and explore with our partners. And this is how we learn things, and soon we would have more footprint in space, so we will learn more. So the agenda for today, we'll go over the complexities that we have currently in space infrastructure. We'll see what we bring to the table with trust minimized infrastructure, and we'll go over our orbital services. And let's start. So not sure if you know, I guess you probably do, but if you missed it, then space is becoming a hot thing right now. And basically everyone wants to put some data center in space, to do some AI computing, whatever. And yeah, there's a lot of PR and hype about it, but the reality is a bit, it's different. So things there are still like, in progress. You can think about the crypto industry 10 years ago, a bit more, but eventually things are not yet completely in place or not easy to work with as a developer, as a builder. And yeah, we hope to address those issues. And with Orbitport, what we want to have is to have a portal to our services, to our infrastructure in space, basically be able to interact with our services and facilitate the entire interaction from Earth to space. And this is the high-level picture of where we at with Orbitport in the bottom. You can see that it's connected to some Earth infrastructure like account provider, and also from the other side to some space infra adapters. That's a typo. And also we hopefully would have also like direct link to talk with space with ground stations and things like that would eventually get to the space, to our satellites. And yeah, today we're gonna jump into many of the things here. I won't have time to drill into each and every topic, but we'll try to do it, and feel free to ask questions. Yeah, let's start. So space communications, basically the biggest issue is that, yeah, you have now latency, that it's different, it's latency and intermittency. So you won't be always available. The satellites are doing the orbits around the globe. It takes somewhere between 90 minutes to 180, and you have communication windows. You can't interact with them all the time. You should be able to do it only once they pass some ground station. And the bandwidth, yeah, is limited. We will get to numbers afterwards, but it's pretty bad. And because we have a strict power budget on the satellite, and basically on the satellite you have multiple subsystems, not just us. We are just being hosted in some satellite, but eventually there are other systems there, and the power is very limited. I know with all the AI boom, they talk about energy from the sun, but as of today, it's still it's not there yet, and it's too expensive to to run things there, and you are limited with the amount of power that you can have, so you're not always on. Sometimes you would be, you need to manage blackouts and things like that. So these are pretty, let's say, are the things to resolve, but let's see a bit more. So currently today what we have, what are the options? So we can interact via ground stations. And do you see my mouse? Yeah. So you can interact directly with satellites using radio frequency, and you can see here like several rings. The first ring is low Earth orbit. You can see the height mentioned here. This is still low Earth orbit, and above you can see the scale. It's not, the scale is not accurate here in the picture, but yeah, this is like pretty almost 10x higher than the low Earth orbit. And this is one way to interact from ground stations. For GEO, we would have higher operation windows, and we would have higher latency because eventually it's more far than the LEO ones. But with LEO, we get smaller windows, but we get lower latency because it's closer. And there is another way of doing this communication, and it's via another network. And this is what you see here in the middle, the LEO communication constellation. There are several companies that basically have spin up network in space, and they help other satellites to interact with each other, and we can also use that. And if we start with ground stations, then as I said, it's like periodical operational windows that you can interact with the satellite. And it has to do with like you as a builder, as a developer, you interact with some APIs, with some cloud systems, and it could get into some mailbox. This is like where the industry is at. But eventually the ground station itself, what it does is to balance the entire demand that it has, and it uses the same, like it has slots that you can be part of them. You need to pre-allocate, but eventually you can be part of some, at some specific point in time, your message will be sent. And the issue with that is that, yeah, on peak demand, we have too much requests going on. With low demand, they actually, if they don't fill enough slots, so they don't send any packet. And basically, it's also another issue. And the bottom line is that we would have delivery delays for sure. So we have several, I didn't mention, but we are working with several partners, and basically being deployed on soon on multiple satellites, and in each satellite you have a different setup. And if we try to look specifically on the RF bands that are used for the ground stations interaction, then we have the UHF for command interface, and we have the S-band. This is what we are heavily using. Basically our data goes through there. And just to mention that the ground stations can handle larger data chunks, but it has the intermediate connectivity. And if you compare to the LEO networks, then yeah, we have maybe a smaller packet, but we have a more consistent connection. These are the most common constellations for these networks, basically like the layout, how do they align on the orbits. And you can see on the left you have the Walker star with a good coverage of also the polar areas. And you have Walker delta. There you can see that the poles are less covered. And you have a mixed geometry, which is everything, both of them. If you look on Starlink, they are the most dominant player. For those who don't know, they have more than 10K in the sky. And they use mixed geometry from this picture. So they are highly available, but they are targeting the, let's say, the residential markets. So It's more like for terrestrial networks to operate rather than networks between satellites or connectivity between satellites. And you can connect to them, on Earth. You have these cool dishes that you can put everywhere. And basically it would connect with RF to their satellites. And then the ISL, the inter-satellite links within Starlink, they would either go with RF, but they are now switching over to laser beams. So this optical inter-satellite links. And this one is crazy from numbers point of view, but it also introduced some challenges that if we put them, like if we try to look how they match to a small satellite, that just not it. It's not there yet. Basically, there are too many integration challenges. The high power and weight that I mentioned before. You would also have vendor lock-in, meaning you would find it hard to work with other providers, with other networks, with other means. And it's optimized for terrestrial networks. And if you look at it for space, for inter-satellite communications, then it's something that is retrofitted rather than something that was organically built this way. So they are getting progress. Let's say if we compare to 1 year ago, then they already have some component that you can install on a satellite. But again, it's still early. So if you look on, let's say, a more friendly project to work with regards to satellite communication is Iridium. They also have a mesh network in the sky. They have definitely less satellites, 66, but it's they operate since the 90s. They are long-term players. And as I mentioned before, they have like good, because they do the Walker Star constellation, which is this one. They have good coverage of the entire globe, and they can operate in places where the terrestrial networks can't. So their band spectrum is a bit, you can see it's mixed. There are bands that are used for, this is user from Earth, basically, messages, and in our case, being below their satellites. They are something like 700 kilometers height, and we out below, like in altitude up to 500. And if you look on the antennas here, if you go to the details of the picture, you would see that the antenna is pointing up. So this is another thing. You need to have your antenna pointing to the right direction, whether it's up for low communications or down from ground stations. So this is also something to consider. There could be multiple antennas, yeah. But it's not always the case. That's the... There's a compute unit on the satellite that takes care of that. It's like not in our jurisdiction, but
like it's a lot of power because you have to impact, like, so you have a limited I don't know, like energy, limited field, so you cannot do it a lot of time.
They do it intelligently, like yeah. So they do it only when they should, like. So Iridium exposes some services for users to interact with. The most common one is called short burst data, or CBD, SBD, sorry. And yeah, you're from Prague with all the... So it's basically like a unicast service. You just send one package to a single device using some device ID, and it should get there. The latency spans from dozens of seconds to minutes, and the payload is, as I wrote here, like this is the amount of bytes we have per payload. I assume, it's if you compare it to what we know and used to today, then it's another problem. And the good thing is that it takes like low power. And another service, it's called Burst. It's a broadcast service. Basically, you can broadcast to a group of satellites that are located in a specific area. And it would help you, yeah, if you want to deliver messages to multiple parties at the same time, or let's say with low latency, then yeah, maybe this is what you should use. But it also has its own latency issues. And for Iridium specifically, they have cloud adapter. It's called Direct Connect. It's deployed on AWS. Their main connection is in the US, but they are available globally. So you can use it basically to work with some queue, to either push or pull your data. And the latency might be better than if you try to do it alone. But yeah, it depends on what service is being used. And currently, I haven't followed, yeah, again, because it's changing every time. So as of now, I think they do support only SBD and some other services, but not burst, as of now. So we saw like the complexities we have with the space infrastructure and how space communication works. So Orbitport part of the story. Well, it has several things on the plate to do. First, it needs to manage the capacity in ground stations and things like that, eventually to pre-allocate if it needs to, so it would have some mean of sending a message at some specific point in time without waiting for the ground station to be ready. And we over-allocate sometimes in order to make sure that some either peak or low demand wouldn't introduce major latency. So on top of that, we also have aggregation and batching, meaning that we don't send each and every message as it comes to Orbitport, but rather we are doing some batching of several messages and basically sending packages of like a set of messages together to reduce the round trips and basically making it easier for us to manage. This
batching also is taking time, so it's a bit longer.
it takes time, but eventually you can plan better like this rather than just react on some incoming request that wants to send something to space and just do it. Because if you do it like that, eventually you will be...
But this batch aggregation is controlled by you, so I cannot batch myself. So
No, it's on our side, yeah.
okay, so you have some kind of algorithm which somehow picks the best batching, etc.
It's not like transactions, like you need to choose transactions. It's like you can do something like more FIFO-based, but eventually you would see, okay, there are some requests that goes to the same service or something like that. So I would try to batch them together. So I would interact with the service once, and I would get 2 responses from it once, something like that. And eventually, yeah, that helps to maximize delivery, but we are also trying to work with different, to send, if we have some message that we want to transmit with high probability and we want it to arrive fast, then we can use several streams to send it, and multiple providers and multiple types of communications in order to make sure it would arrive fast. But it also comes with a cost. So on our side, we need to balance between the reliability and the cost of the solution. So at the end, what Orbitport does for others is to streamline the connectivity with the satellites. Basically, if you come from outside and you talk with Orbitport, you wouldn't always tell that, yeah, okay, it talks with the space and wait for response. And it's actually a pretty hard thing to do. We are not there yet, but this is our goal, and this is where we aim to be at. And if we look on the entire story, so what we get here is if you compare to the TCP IP stack, then on the physical layer, we have the RF link, and it could be either like from ground station coming or from LEO networks, but eventually this is the first layer. On top of that, we have, I called it the embedded subsystems. Basically on the satellite, once you get some packet, once the antenna reads some packet, it needs to send it to the right subsystem on the satellite. In our case, it would be us, the right subsystem. And the network side, this is what we just talked about. So again, it's like a complete layer that we need to do our logic there. We are running in a TE. I will go into it very shortly. And we are utilizing multiple vendors and providers. So eventually, it's like, you can think of it like batching, aggregation, all those things, but also routing and basically managing all the different providers. Then we have the transport layer, which on our side, it translates to we call it a tested transport. Basically, what we get is a secured connection between TE on Earth and TE in space. And yeah, again, we would jump into it very soon. And on the application layer, we have our platform, what we have on the satellite, which provides, it has like its own services and things like that. So we need to find our way within the satellite, within our compute unit. So yeah, I promised TEs. So what about the trust? I mentioned until now only like all the networking, communication stuff, but eventually, and yeah, we are doing the aggregation. It's a pretty, let's say if you have something which you want privacy for that action, if we are doing all this batching and things like that, we are losing that. And basically what we want is to run on TEs on both sides. And on Earth side, we are running on TDX. And if we'll do like a short, maybe yeah, before we jump into other things, we'll do like a short introduction to TEs. So TDX by Intel, it's supporting virtualization. That's like a cool feature of it. And basically what you get is isolated VMs running on a single machine without having none of the VM access to other VMs. And also the hypervisor, no one can access the memory of some VM. And it has a remote attestation that allows us basically to verify what software was running on it and that the hardware also matches it. And if we look on what we have in space, TDX, yeah, it's good for Earth deployments, but it's not fit for embedded systems and things that you want to be more optimized with. And it has another big drawback. We'll get into it. So with ARM Trust Zone, things work a bit differently. Basically, it separates a single CPU into two main regions. One is the normal world, where we have, it should be like some trusted operation system, but at the end, this could be any Linux distribution running there. And we have the secure world, and there is, let's say, a mini operation system. And we have those two on the satellite. They are working on some device. We'll see it soon. But it's a single core device. So basically, you have another component called the secure monitor that takes care of context switching between those two. The context switching is done with, I didn't write here, it's done with exceptions. So whenever you have some exception, for example, in the normal world, you go up to the secure monitor, and it can decide what to do from there, whether it's a real exception or you just need to context switch to the secure world. And you can pass like that parameters and everything. And eventually you have also like, you have ability to control the peripherals, let's say the things that you connect to it, the devices, and basically ensures that if some device is being used by the secure world, it won't be used by anything in the normal world. So we have these two, ARM Trust Zone and TDX. And if you look on the infrastructure for Orbitport, then again, it's a TDX-based runtime on Earth, and in orbit, we are running on ARM Trust Zone. Basically, we have a mutual remote attestation where we validate the attestation from space on Earth and vice versa. And we have verifiability. So whatever is being sent, we know that whatever is being processed, we know that it was running on some specific software, on some specific hardware. And yeah, we know the origins, where it came from. So if you look on the layers of trust for Orbitport, what we're doing is to have our own OS image. We use mCOSI to build it. And on top of that, we are running K3S. And for that, we have our images, our container images that are being built with Docker hardened images. Basically, I'm not sure if you know it, it's a pretty new feature of Docker, but they created some, it's also like tools and repository and everything for hardened images that basically you can track the entire SBOM, and you have all the dependencies, everything is pinned with versions, and it has some other like standards than the normal Docker file that we know. And eventually, we connect these two things, these two pipelines. Whenever we put some code to our then finally we get a Docker hardened image that sits on Docker hardened image repository rather than Docker. And what we do from there is on the we take all the images that we got, we create the service sets, K3S. Behind the scenes, we use containerd, and eventually we have the output is that we have a pretty we strip off everything that we don't need from the operation system, so we have a pretty thin image that we can boot on on any VM. But in our case, we go and run it on a confidential VM on GCP. This is provided by them. Basically, you can think of it like having some spot of some compute that runs TDX, and therefore we can run as a VM on this infrastructure. And within what we have running, specifically we have Orbitport, of course, but specifically we have some reverse proxy to pull off the TLS termination and to have a more less like the space environment, what's going on there, how it looks like. So first, what we have there. So our unit on the satellite, it consists of a Raspberry Pi, USB Armory. That's a cool secure device with ARM charge zone on it. If you look on the hackathon, you would see in our track, you can play with it in one of the tracks. So yeah, take a look. And we have some TPM on it as well. And you can see, okay, so you can see here on the left, this is the actual board that we would have. Basically, it's a Raspberry Pi on top of some other board to have all the components integrated in an optimized way. If you look on the left, this is a stack where eventually the board sits, and you can see that it has like these copper stripes. This is what we use for heat dissemination. And this is how it looks like as a box. And eventually it arrives to some small satellite. In this case, this is a CubeSat. And if we look what we have inside, then what I explained before with the normal world and secure world, this is the USB Armory connected to the Pi. On the Pi, I'm not showing you everything that we have, but just so you know, we have an operation system that we also made our own using Yocto. And on top of that, we have some, it's not just one single app, but we have several relays that helps you to get to the secure world, eventually to the USB Armory. And on the USB Armory, we have another two secure elements that we use. And I think we can see here, okay. So the setup, once we want to set up some satellite in the sky, and to be sure that from our point of view, we know that we are talking to that satellite, we need some proof that the vendor didn't just put the Raspberry Pi in their garage and saying, yeah, it's in space. So we want to have something stronger. So what we have is, let's say once we launch something, then we only in the sky, we generate 2 keys. And these 2 keys are generated from different devices, the ones that we see here, the SC050 and the Tropic 01. And we use those keys in order to eventually participate in some protocol called SIP, Security Execution Assurance Protocol. This is a protocol that we worked with common prefix to have some defined flow for us whenever we want to boot or provision some satellite. And eventually how it works is that from the ground stations, you would have some form of challenge response ceremony with several ground stations. And as a satellite, you need to interact with several of these, and then you get a certificate. And this certificate, basically, this is like the attestation. And ongoing here, it says, still not there. We need to talk like about design stuff, but yeah, we would also have like something ongoing with regards to this proof. So it wouldn't be like just a one-time. Currently, with the protocol, it's a one-time thing, just when we provision. But we plan to have it something more that occurs periodically. A nice picture, I think I mentioned most of it, but yeah, just to see the layers themselves. Here I forgot to put Yocto at the beginning, but eventually, and I didn't mention secure boot, so what we would have in our system is that besides that we would create the image, we would also run secure boot to ensure that only image that we made can be run. And we would have the same secure boot ceremony also with other up there. It's something that we have and signed, and only these can be running. Like no one can just put their stuff or manipulate our software. So eventually we get something like a proof that, yeah, we know what's running, we know where, and yeah, now we are good to go with regards to security. So yeah, we've seen all that, and eventually, yeah, we want to see what we can do with all these things. So if we look on the architecture of Orbitport, then if you look on the left side, we have some user that can interact with the gateway. The gateway would route the request to the right service. Currently, we support only CDRNG and KMS, but soon there will be more. And in general, we have here more components, so the authentication, as I mentioned before. Currently, we have the account provider completely isolated from Orbitport. But yeah, it's just to get started. Afterwards, we would connect it. And on the space infra side, so we have connectors, which basically helps us to differentiate between the different APIs, the different components of each provider. And it could be like the same provider, but different interface. So yeah, it's also like very helpful on that front. And we will get, yeah, there are several things here that I still need to mention with regards to CTRNG and KMS. But we have more components. For example, we are working with IPFS to have some distributed storage. And yeah, I think that's it for this picture. So CTRNG. CTRNG stands for Cosmic True Random Number Generator. And basically it relies on entropy that we gathered in space. There is some sensor that helps us to track over space radiation. And I can't really tell how it's really working, but it's basically provide us some random number that is based on some phenomena in the sky, in space, no one can access to. And basically it gives us a real, true random number. This is like, and we would see soon that we also have like a way to validate it. So 1 second. So if we try to play a bit, if we try to play a bit, and we can start with the docs, but let's open CTRNG. That's a bad link. In the docs, you can find some guides how to work with our SDK. We have an SDK in TypeScript, and specifically for CTRNG, we have also in Rust. But generally, yeah, we plan to support all the Rust, Go, TypeScript, whatever. And as a user, you need to provide some client ID and client secret, and you are good to go. Basically, you can ask for a random number, and you will get something from space. We also have another option without credentials, and this would go to what we call a public randomness beacon. The randomness beacon is a chain of blocks with random numbers in it. And what happens is that you can access it from anywhere. You don't need any API keys, you don't need anything. And we post every, I think, 5 minutes, we post a new block there with new randomness. So you can basically use it as a seed for your system. And yeah, and you can manipulate the randomness because eventually it's public. But yeah, you can work with it without anything. So these two cool options. How do I get back? These two cool options are available through the SDK. And if you look 1 second on this project, basically we have integrated the CTRNG as a seed for threshold libraries. And we use this, this is the library itself. What we did is to follow some interface, so some trait, and basically be able to, so others would be able to work with us. And basically you can give our component as a RNG generator, and it would work. And basically what we are doing is to, it's also related to the randomness beacon with IPFS. What we are doing with that is that we use mixed CTRNG, and mixed in the sense that we are taking a real CTRNG from space, and we use it as a seed to generate more random numbers. We follow, you can, I think it's written here somewhere, but whatever we are doing is we are doing the derivation based on Cha-Cha, meaning that we are trying to take some random seed, generate multiple numbers from it until some it was used too much or things like that, and eventually the user would get a random number that is also based on the cosmic one. So on our side, we did lots of investigations on how can we prove it, how can we prove its true randomness. So we have integrated here several statistical verification tests, and you can run it yourself, and you can check the repository. We actually have a repository for statistical verification. In order to really do some real tests here, you need lots of data sets. So with something from space, as you can imagine, it might be hard to get enough data. But if you have something that you can provide million or more items from it, then yeah, you can run these tests, and basically you can verify that your randomness is truly random. And I think that's it with regards to CTRNG. If we look on KMS, then we offer like a very special solution, because if you look on existing KMS out there, on Cloud KMS or Ashiko Vault, things like that, eventually you have the chicken and the egg problem, where you need to store some root key for this KMS. You need to store it somewhere. So you either store it in some other KMS or several KMSs, but yeah, eventually you're stuck in like some sort of a loop. So you trust some cloud provider, because you don't need to worry about their root key. So they know how to worry about it. So you use some cloud KMS or some HSM. But both introduce issues, and eventually you have both, like if you look on the cloud KMS, then you have a provider lock-in regulation issue. And if you look on HSM, then yeah, you trust some operator. So eventually this is a problem which we aim to solve with our version of KMS, which can run in space. And basically we run on top of OpenBOW. And those who don't know, OpenBOW is the open source version of Ashko Vault, which has turned business licensed since 2003. So yeah, OpenBOW, it works the same. It works with the same architecture. So it has it's called Go plugins. They allow you to extend their capabilities with Go code that you write, and you follow some interface, and basically you can be running as part of OpenBOW, your code. So what we did is to implement a plugin for Ethereum. So you can do key management and signing. And we are also planning to do it for Threshold DCDSA, and for PQC. And hopefully we can do it for other things that we would see in the future. And Orbitport in this case is the orchestration layer of it. So you have OpenBOW with plugins, and this deployment also, it's like both on Earth and in the space. So in the space we are also running OpenBOW. And basically with Orbitport we can orchestrate all the processes that needs to happen. And in the future we would have the MPC flow orchestrated from there. And we would have, as I mentioned, like an hybrid deployment where some of the nodes would be on Earth and some in space. And in both cases, yeah, we would be running within an enclave, or at least some of the processing would be done within an enclave. If we open the docs. Then in the docs you would find a pretty detailed also like examples, but also what are our capabilities. Let me jump right into it, 1 second. So basically you can see what we support. We support, of course, what comes by default from OpenBOW. This is this transmit scheme. You can see there are many algorithms that are supported, and we also include Ethereum as well. And how it works as a user, again, through the SDK, but you can do it by yourself. It's just HTTP code. So you need, again, here, this time you must have a client ID and a secret. And once you have those, you can connect. And basically you can discover what are the capabilities of the current deployment of the KMS. It will change over time, and it might support multiple KMSs, but for now we have like a single entry point that should give you back the existing capabilities, and according to that you can take a decision on your end. So whenever you want to interact with it, you need to create some key, right? So there's an API for that. Then whenever you call, the key is completely generated completely out of your site. You as a user never see the key, and you never get it raw. And in general, whenever you want to work with it, you can perform the cryptographic operation with our plugins within OpenBOW. So it could be decrypt or encrypt, and it could be signing. And besides that, we allow you to rotate a key. And basically, let's move to another one.
I'm just really sorry, we're running a little bit out of time. So in 5 minutes, if maybe just feel like for questions.
All right, so let's jump really quick. Let me just show you.
So I don't know if there's like questions,
Yeah,
but
sorry.
yeah, maybe. Thank you for the presentation very much. So if you could clap together. Anyone has a question for? Does anyone have a question? Oh,
Thank you, Amir, for the presentation. Please, what are the challenges of having the computational platform on the orbit regarding the radiation and deorbiting?
Yeah, we didn't get into the satellite things too much, but yeah, whenever you're in space and we're using like customer silicon, like not hardened devices for space, so we need to have some coating and protection. You saw it with the aluminum box. And eventually, space radiation, it has like there are several types of things that can go wrong. One is the degradation of the hardware. So this is where the aluminum box helps. And afterwards, you have phenomena like bit flips. So it can actually flip some bit in your memory, and then some computation, sorry, 1 second. Some computation can be wrong, for example. It would be corrupted. So you need to handle that on the software level. Like you need to either run a single computation multiple times, or to have several components, exact components that would run the same computation. So you would actually be able to validate that this is the result. And well, there are many things around the satellite things. So, but if you focus only on radiation, then I guess on our side, we also take care of, let's say, the storage, whatever we put in the memory, we take into account that it might get corrupted. So redundancy is the king here. Like you need to understand how you have redundancy in your architecture on both hardware and software. That's the, yeah.
You're running your software on like the normal Raspberry Pi, so there is like a standard RAM memory, so there is no memory which is try to avoid with bit flip and etc. You do everything on the software level, right?
Let me go back here.
Yeah.
Yeah. So you can see here on the left, this is the actual board, a picture of our board, our PCB.
So your PCB is on top. Like what exactly is this doing? Because on the hood is Raspberry Pi, classic one. But what is the top level? What is this shield does?
So you can see it's connected to it here.
Yeah, yeah.
And also via this USB sharing dongle. And basically, we have several peripherals that we connect to it. The USB armories, for example. All right, we have 2 USB armories. That's 2 USB connections that we have there. And we must have this set up proper for space.
Okay.
We mentioned radiation, so there is also vibration in space, right? So USB, things like that, it wouldn't work the best over there. Yeah.
Yeah. Thank you really much for the presentation. We are unfortunately running out of time, so thank you again very much.
Yeah, and come find us in the hacker room.
Yes. And we're going to be moving to